Hello everyone, I am Jinghao Ye from Taiwan National Zhongqing University. Today my topic is effect of extrusion temperature on the physical mechanical properties of unidirectional wood fiber reinforced polylactic acid composites components using fused deposition modeling. In the last decades, additive manufacturing (AM) has been a promising technology in various applications. It enables the automatic fabrication of products or functional components with complex shapes at a low manufacturing cost. Among all different AM methods, fused deposition modeling (FDM) has recently gained popularity and achieved widespread use as the manufacturing process of desktop 3D printers. It allows solid parts with a 3D geometry to be formed by assembling successive layers of conventional or biodegradable thermoplastic material. A few studies have reported that the quality and mechanical properties of FDM printed PLA components are significantly influenced by various processing parameters. Among them, the mechanical properties of printed components with various extrusion temperatures has been examined but not intensively investigated. During FDM printing process, temperature is generally set in a range of 200 to 230 degrees. Therefore, properties of the components that are printed from a wood fiber reinforced PLA composites are clearly changed. Hence, the purpose of the present study was to investigate the physical and mechanical performance of the WFRPC components printed at a different extrusion temperature. For the material and methods, the commercial WFRPC filament used in this study contains 40% of cedar fiber. The other properties are shown on the left-hand side. Printing speed, platform temperature, print width, and layer thickness are also shown. 4 different extrusion temperatures were used to print out the samples, which were designated as WFRPC 200, 210, 220, and 230. For the printing components properties, density, moisture content, water absorption rate, thickness rolling rate were determined, and also the tensile, flexural, and compressive properties. Besides, SEM surface color and surface roughness was also tested. From the surface appearance, we can see the color turned from light brown into dark brown as the temperature increased. Studies showed that darker color resulted from the changes in extractive, the formation of products from hemicellulose decomposition, and formation of oxidation products. On the surface color parameter, the results showed that a decrease in the L star value and an increase in the A star value were observed as the extrusion temperature increased. In contrast, the B star value was not influenced by the temperature. This result indicates that the extrusion temperature affects the color of wood fibers in the WFRPC components. Former studies showed that the results from L star and delta E star are attributed to hemicellulose degradation. On the physical properties, we can see that weight and density increased. According to the previous study, the weight of the printed sample was increased by reducing the viscosity of the WFRPC filament as it was extruded at a higher temperature. However, the volume, moisture content, and surface roughness wasn't influenced by the temperature. After 24 hours of soaking, water absorption rate and thickness rolling rate exhibit no significant difference among all samples. This may be accounted for by the similar compatibility of PLA matrix on the surface of the wood fibers among all samples. For the mechanical properties, we can see that tensile property and flexural properties decreased as the extrusion temperature increased. It can be attributed to the formation of acidic products from hemicellulose degradation. However, compressive strength and internal bond strength increased. On the appearance of the compressive failure, we can see the damage evolution of all samples were caused by the buckling and cleaning of filament segments, leading to debonding between their interface. Load carrying capacity was mainly influenced by the internal bond strength between filament segments. WFR 230 exhibit the highest internal bond strength value is mainly attributable to the strong interlayer bonding between filament segments and the better compatibility of fiber and PLA interfaces compared to WFR-PC 200, leading to a higher compressive strength. From SEM, we can see that there are more pores in WFR-PC 200, which represents the fiber pores, but for WFR-PC 230, less pores were observed, showing a better compatibility between wood fiber and PLA, which leads to free fiber breakage. For the conclusion, an increase in delta E star was observed as the extrusion temperature increased, and most of the physical properties of WFR-PC 230 didn't show significant difference compared to WFR-PC 200. The tensile and flexural property decreased with an increasing extrusion temperature. The compressive strength and internal bond strength increased as the extrusion temperature increased. And in the SEM, we can see that higher extrusion temperature show better compatibility at fiber and PLA interfaces and stronger interlayer bonding. That's all for my presentation. Thank you for your listening.